月5月29号，隔得比较开。哦，挺好的。上课的多。上课这一门我是最方的，基本整个3门也方。就是那个光子那个。甚至这里面我不知道后面讲的东西有些什么东西。拿了一下他的一个学的因为这是讲的好像是那个中后习题。那个你有书吗？没书我不我是因为我有中文，后面有英文习题。现在我把那个书全扫一遍。我有书吗？我开给你。我有书吗？我有那个中文版。英文版也有，中文版的线版。但是答案是有的，答案是上面会有一些发给你。你们现在看一下，可能有。上面没有，挺好的。书我觉得看书好用，看书感我觉得有点吃神。但中文版你还有时候有些词你还要想一下，比如说像这个，像这一般就是像你提的就是打的，然后再把它提高了。这个我觉得就是有点搞不定的感觉。算是时间感觉是来不及了一样。这天还在忙，昨天那是扯。发现自从学会打目标前之后，变得有点放飞自我。去那里不要打中文，只拿中文我们的在。对，太软了，就没有形了。这个就太亮了。我写的还是防火太软了。这个是在商学的，你当时头脑没看到，是在头脑。我们的 lab 其实挺好的，但是不能裁的。但这个商学院的可以裁的，而且是白纸。这样是把新的东西打进去，新打进去要买新的。对，就是它可以设置各种各样的，你可以跨过去啊，首先把这个对。不是你，因为每次上班那个也不一个差不多。从那里走到火车站是15分钟，对。然后你提前5分钟到，然后到火车就是转到汉斯，所以到2个站，差不多得1个小时20分钟。对。然后就像这个1小时40分钟的，1小时40分钟的，然后这样的话你再从 Kiss 走到斯诺克站，20分钟，你得2个小时。不止2个小时，一趟，反正我4个。不止2个小时，因为它那个火车那个定点不会让你享受定点，它一般会定在7点10分。这就是6点50时，这样6点50时间。2个多小时。我想好像那种我有一天晚上什么小说什么下来，只是在火上听，或者在火上睡觉。我应该讲吃饭。这个咋搞？他是不是 就看一下，最后一个它是跟前一个有3天时间打，应该蛮喜欢的。因为我没想到把给你考，所以我就没看到他最后的那个推荐，他那个复习课很无聊。我觉得他 PPT 写的很清楚，然后每次都要叭叭讲。因为我现在一码学，所以说要码这个。什么时候买的？哪个卡？也是有状态。为什么买这个新的？多少钱？你买了多少钱？1000多人民币，便宜的吗？那这个新的呢？新的还是最起码最低码的你也不在那边了，根本用你不用在那边，就太低了。是18年要快结者。你不是考虑那证吗？2年前吧，考的暑假本查，这个不是取消了就取消了，自娱自嗨，我礼拜日就取消了。日本这块是，但是做快不好考哎，做快省心自己做很难。
Sorry, folks, I got lost along the way. Okay, it's pretty hot in here.
no windows. So it's a bit like lecturing in a hole. Okay, but anyway, we try to put up with it. I'll try to be as quick as I can. Okay, here's the revision questions. They're in no particular order. The one thing I would like to point out to you straight away is there are no questions on machine learning. Okay, so you don't have to know anything about that. I have said it before, but just to reinforce. Remember, we did it because it was a good skill to be exposed to, as far as employers and so on are concerned. Okay. Shall we go through the questions one by one and see what happens? Okay, the first question is a simple securitization arrangement is used to turn loans into asset-backed securities in 3 different levels, or what we refer to as tranches: senior, mezzanine, and equity. Describe the waterfall feature of such an asset-backed security. Again, the English here is what might make life difficult for you. Okay. Where's Matthew? We've only got one spare chair, and Matthew's not here. Anyway, I think we should just punish him. If he does come, we make him sit on the floor. All right. So, what was I talking about with regards to the waterfall feature? That was the way these things are done. That essentially, if you remember, I think I drew a brief diagram last time. So, we got our champagne glasses. And so on, down the different levels. And what happens is, in comes the money. It fills up the first glass, it then overflows into the other bits, and the other bits like that. Okay, so that in fact, if we run out of money, these guys down here get nothing. Okay, so that's essentially what the waterfall is. But let's look at a more descriptive nature of it. So the waterfall feature is a set of rules by which the tranches receive their money. Okay, that's, that would be tranche 1, 2, 3, 4. So that would be the senior tranche. Okay, they're the guys that'll get the money first. And as I say, it's an order of seniority. The cash flows of the assets, backed by an ABS of some sort, are used to pay the higher tranches, and then, if it's possible, we start to pay on the other levels as well. Does that make sense to you? Okay, so there are 2 things here. The diagram says it all, okay, but you have to write it down. Okay, so that's where the difficulty comes in something like this. It's quite easy to get all of the English muddled up in your head. Okay, so that's clear. I mean, even if you draw a diagram like that would be useful. But that's the descriptive nature of the waterfall feature. Are you with me on that? So easy to see inside your head, but maybe not so easy to write down. So be careful. Okay? Are there any questions about that? Does it make sense? Okay. Part B of the question. The portfolio consists of 100 million nominal loans, split 65 into the senior tranche, 23% into the mezzanine, and 12 is in the equity. So if we look at the different loans, so could be 100 loans, all packed together. They all add up to $100 million.
And they're then packaged by an investment bank of some sort, or a shell company of an investment bank, into, so this gives us a flow of money. All right, this is what these guys would buy. And they're characterized by different rates of return. I mean, the rate of return on this one would be pretty low, okay? Whereas the rate of return on this one would be pretty high. But along with that comes risk. So there's a lot of risk in this tranche, and there's very little risk in the, normally, there's very little risk on the top one. Okay, so that your $100 million gets put out in these different tranches. So if everything goes well, if the 100 million gets paid out, then that's what each one would receive. However, if some of these loans start to default, then there's no longer 100 million. It may only be 50 million. So that 50 million will go to these guys, and these guys will get nothing. So that's what happens. So this diagram is connected to this idea. Okay? Does that make sense? So it's a fairly simple structure. Just you've got to be careful about the way you write these things down. You all right with that? Anybody want to ask any questions? Remember, the understanding of this is very important, because this is what caused the financial crisis. So you might think, well, that's easy enough to remember, but it led to a complete and utter disaster and almost brought the world economy to a halt. So these things are not minor by any means at all. Okay? Let's see, does that end question one? Yes, it does. Okay, now, question two is more of a calculation type question, but it's sort of how, it's really asking you, how does a CDS work? Okay, so a CDS, so a credit default swap. Remember, this was a way of insuring yourself against the credit risk. And that's where these guys on Wall Street made a fortune. They were able to buy that insurance when nobody else was interested in buying insurance. They bought the insurance on loads and loads of companies and loans. And of course, when the whole edifice came falling down, these guys made an absolute fortune. Okay? So, you've got a credit risk swap. A credit default swap is an insurance policy. And let's see the details of it. Well, it requires a semi-annual payment. So in other words, if you want to hold this insurance, you have to pay a certain amount of money. That amount of money is connected to two things: the principal amount and the number of basis points attached to that particular bond. So in this case, the bond is running at 65 basis points. So you're going to have to pay 65 basis points every 6 months. Oh, no, sorry, half of that. It's basis points per year. Okay? How do you convert that into money? Well, it's 65 basis points of the nominal amount, which in this case is 100 million pounds. Okay, so it's 0.65 of that calculator per year divided into. Are you okay with that? And what happens? The default swap was settled in cash, because remember, you could do it in cash or you could do it in bonds. Sometimes the other side would just deliver certain bonds to you, which you would do. That's another story. A default occurs after 3 years and 4 months, and the calculation agent estimates that the price of the deliverable bond is 45% of its face value. So the recovery rate is 45%. Describe the cash flows and the timing of the seller of the CDS. Okay? And that's the question. It's probably longer to read it out than it is to answer it. So what you've got to do is the seller of the CDS receives the insurance premium. Yeah. So what is that insurance premium? Well, as I said, it's 100 million times 0.65% over 6 months. Okay. So this guy receives 0.325. And for a long time in the market, this was a sure thing. These insurance companies were making lots and lots of money. They just didn't see the disaster that was about to happen. So they saw a steady income over a long period of time, like any insurance company. I mean, the fact that the insurance company works on cars is that we're not all going to have an accident at the same time. I mean, how unlikely is it that we're all going to get into a car this afternoon and bash into one another as we leave the university? Okay, it's highly unlikely, but that's what happened. Okay, so just looking at the surface, the insurance companies were happy campers. They were making lots of money. Okay, and if a default did happen, it would only be now and again. Of course, what they didn't realize was the concept of contagion. That as one person had an accident, somebody else had an accident, somebody else had an accident, and before long, everybody was having an accident. And the people looking at the accident also had insurance on the people having the accident, so they all had to be paid as well. Okay, and that's essentially what happened with the crisis. At default, which is at 3 1/3 years, the seller receives part of the payment. Because remember, these payments, these premium payments, are made in reverse. So 1/3 of the way through the year, he hasn't received his money yet. Okay, so he's due to receive 0.217, and that comes from the 100 million by the basis points by the time period, which is 1/3. Okay? Happy enough with that? That's the good news for the seller. The bad news is default takes place. And if the default takes place, that means they have to come up with the cash of the outstanding disaster. So remember, it's not the whole 100 million that they have to pay, but they only pay the bit that can't be recovered. And the recovery rate is 45%. So the amount that they have to pay out to the holder of the CDS is 55 million. Okay? And that's, of course, these guys made their fortune. Because it was 55 million times 100, more, 1,000 companies that went bankrupt. Okay? So they made a huge amount of cash. And of course, it was from the insurance companies that they made it. So one of the biggest holder of CDSs was Goldman Sachs. Goldman Sachs was naughty. It knew that this was about to happen, and they quite happily sold CDSs on to other people, insurance companies. So AIG, the American insurance company, collapsed, basically. And that's when the American government had to step in and save the company completely. And then the domino effect all over the world, because investors just couldn't get enough of this. They were so excited about these ideas, this idea of securitization. It was a huge market. So, but a real story to tell there. But that's it. So as I say, it actually takes longer to read the question than it does to answer it. Are we okay with that? Okay then. On to the next one. Question 3. Well, yeah, this is your interest rates. So it's an OU process, all right? And you've got another process X, stochastic process in terms of the interest rate, which remember is a stochastic process as well. Okay? You're told that the function f is given by that. Use Ito's lemma on f. So the first part of it should be doable, all right? It's a simple matter of using Ito's lemma, okay? So I've got to find all the different bits, put it into Ito's lemma. In fact, no, I don't even use Ito's lemma, not yet. What I do here is I just differentiate the thing up. Okay? So I differentiate this guy here. So it's a product rule. So it's f, okay, times dg plus g times df. Are you with me on that? Remember the old, this is hopeless. Let's try this one. That's even worse. df g is equal to f g plus g df. The product rule. And I use the product rule. That's it there. Okay, so those first two terms come from that. The last term, although it's complicated, is the easiest to deal with because differentiation and integration cancel each other. So that this one just means the integral sign disappears. And you're left with RT dt. Are you with me on that? No? At that point, it's just a matter of putting in what f is equal to. And yes, what f is equal to. Sorry, let's read the question, just to be sure. Sorry, it's a b that we've got here. So here's the b, and no. So it's just this part here. Can I? No, I can't. Ugh. Sorry, I can't highlight it. So, I mean, that's where I find b prime, because when you look at the solution, you have b prime there. So I just put that b, I work out what b prime is, and then I put it into that part, and that's what I get there. Okay. And then I jiggle it a little bit. I bring the dt terms together and the dw terms together. And that's where I get the at and the bt. Okay, and in the question, it actually defines what at and bt is. So it gets down to that. Okay? Now you have to go through that bit by bit and just see exactly where each of those things are coming from. Then the question tells you to apply Ito's lemma to f, where f is this guy here. Okay, that's in the question itself. So I need little a, I need little b, I need the first derivative of f with respect to t, I need the second with respect to, it's probably what, r, and so on. So I plug those in. Okay, and I get down to that. So I just work out what this guy is, what this guy and this guy is, and I put that in there. At that stage, you know, I do the same trick. I bring everything that has dt into one term, everything that has dw into the other term, and then I say, if this is a Markov, then the drift term must be zero. So this guy here has to be 0. Which means that that differential equation, and it is a differential equation, has to be equal to 0. So if I go down a little bit, there we go. There's the differential equation. And I know what AT is, and I know what BT is, so I have to solve this differential equation. And that'll give me a value for, I think that's B. That'll give me a value for B.
Sorry. I got a question.
Yeah.
For the last line for the DF, like the drift term, inside the drift term,
Right.
is it a B term? Is it negative? Should be negative, isn't it?
Which one? Which one are we
For
talking
the
about?
drift term.
Okay. So we take the F outside. Let's just check. Sorry, actually, so that everyone knows what we're talking about here. We're looking at that line, okay? And you can see there's a common vector of F. So we can take that F outside.
Yeah.
There it's there. Now what are we left with? It should be minus, and I think that's B, not B. I'll probably change it somewhere. That's B tall. Okay. And it means that should be I think there should be a minus sign there, okay? But that's okay. Because I've taken it across. What should we better do it. Okay, sorry. Minus beta prime minus AT plus a half BT squared, yeah, equals naught. So bring that across and I get beta prime is equal to, oh no, it's minus AT plus a half BT squared. So that's what that line there, that should be a minus sign and that should be a plus sign.
Yeah, but how can you erase the minus sign?
No, I just took the
yeah.
minus beta cross the equals sign. Are we okay with that? So a bit of a jiggly one, not the most obvious thing. I did warn you that interest rate models are the most complicated of the models that we face. And then of course I know what AT is and I know what BT is, so I can put all of this back together. And then I can try and solve that, but that's not easy.
So the answer down there is not the correct one.
I don't know. I've forgotten what AT is and what BT is to get to this point. But that one's wrong. That should be minus, and that
Yeah,
should be
because
plus.
I checked your answer for the previous year. It's the same error for the answer.
Okay.
Yeah.
Yeah. But sorry, no, that just means I can have copied something. But look, some years people come back to me and say things, and some years they don't. And if they don't tell me, I don't change it. And if they do tell me, I'll probably forget to change it. But it's a simple thing, it's a minus sign, okay? It shouldn't confuse you, all right? Because I'm not actually solving that differential equation. I'm just saying, that's the answer, what we have there. So we could take it further, but we don't have to. Is that okay? So it's a nasty question, but interest rate questions are nasty. What I would say to you is make sure you know the general forms. You know, the idea that things, it could be a geometric Brownian motion that the RT has to satisfy, but it's more likely it should be a mean reverting process, which means that you're going to look at the Vasicek or the CIR or the Hull White. So those three are the main ones. The other thing that you should know about, because the computation can be quite awkward, is make sure you know the basic properties of interest rates, or interest rate models. You know, I don't know whether there is a question there, but listing the attributes. You know, it must be mean reverting, that it must be arbitrage free, all of those things. And we have done them in the notes. Those sorts of things you should know. Because if you know them and the question's there, you can just write them down. Does that make sense? So make sure you can do that sort of thing. Okay. Question 4 says, read your notes. Barrier options. Okay, so look, I mean, if a barrier option question comes up, you should be extremely happy. Luckily enough, I've completely forgotten what's on the exam. Okay, so I can't tell you whether it is on the exam or it's not, for any of them, because I've just forgotten. I just know we cover about 65% of all the exam. So, you know, as I say, as far as the barrier is concerned, the calculation is very simple. It's almost the same as the binomial tree that we did in semester 1. Okay, there's very little difference between the two. So all I would say there is just go over your notes and check some of the examples that we looked at. Hull will also have examples, so I'd say just have a look at that as well. Does anybody want to ask anything specific about question 4? Maybe if you tried some and you got the wrong answer, or you weren't sure about anything. Once again, in the barrier option, you cannot use the big formula. You know, like C naught equals e to the minus 3 r delta t, okay? Because it doesn't work that way. Some of the nodes will be 0 because they're above the barrier or they're below the barrier. Okay? So just be careful about that. All right, then let's look at question 5, if there's no questions about that. Now, in question 5, I can give you a kick in the ass. Okay, not all of you, but some. Why? Because very few people turned up to the math lab laboratory when we did this. Okay? So if this question looks totally foreign to anything you've ever done before, it's your own fault. You didn't come to the lab. Okay? So let's talk about it. It's trying to work out the value of an Asian option. Now, working out the value of an Asian option is not a simple calculation. Okay, it can be quite difficult. And first of all, you've got to know what an Asian option is. Asian options are average options. So the strike price, or the way we work out S capital T, is based on an average. And there are 2 different averages that we tend to associate with Asian options. So Asian options, and they're very popular, okay, because the risk attached to them is less than ordinary options. Asian options, you've got 2 different types of, you've got arithmetic, and you've got geometric. Now, it turns out, a bit counterproductive, or counterintuitive, I think. The geometric is the easier one to use. And for that guy, there is a formula. Okay? For this one, no formula. Okay? But using Monte Carlo methods, I can find an estimate of this from this guy here. So this one I can work out, but if it's an arithmetic Asian option, I don't have a way of doing it, but numerically I can use this one to predict what that one is. And that's what we talked about in the lab. So let's look specifically at the question. So in the main, so I try to set it up. In the main, there are 2 types of Asian options. One where the average price of the underlying asset is based on the geometric mean, and the other depends on the arithmetic mean. In the former case, that is in the first case, the geometric one. So in the geometric one, there is an analytic formula for the price of the average Asian option in the Black-Scholes framework. It's not particularly easy, but you can work it out. And I've published a couple of papers working with that as well. But there's no closed form solution for the arithmetic average. Explain how the controlled variate technique can be used as a variance reduction procedure for evaluating an arithmetic average Asian option. Now, to say, if you haven't been to the lab, that will make no sense whatsoever. Okay. So let's just look at the solution to it. The solution is not terribly big. Okay. So the controlled variate technique is when you compare solutions of like with like. And you make the difference, and that difference is the bit that you add on to the one that you want to estimate. Let's see what that means exactly. The controlled variate technique. So it's a technique used in Monte Carlo. One of the problems with Monte Carlo is it takes up a lot of computation. So anything that can sort of mitigate against that computation is very useful. And what they refer to there is that the convergence to a particular value, if we can get there quicker by using some method, then that's a useful thing to do. And that's what the control variate, and that's why you say it's a variance reduction procedure. Again, if you read your notes and you go to Hull, you'll see we talked about variance reduction in class. And the reason that we can do that is because we can use the similarity, they're both the Asian options, the similarity between the analytic and the arithmetic. So I can actually use one of them. So that's basically what I said on the board. I use this one to estimate that one. Okay? So in the simulation process, that's in the Monte Carlo itself, you simulate an approximation for the arithmetic option. Okay? Which may or may not be very good. The FG I can simulate as well using Monte Carlo. And that will give me two estimates for the options. You with me? So based on just Monte Carlo, in other words, just a big sledgehammer and just doing things over and over and over and over again, we get estimates for an for an arithmetic option and the geometric average. But remember, we have an analytic solution for this one. So I can compare this difference with the analytic solution. Yeah? Are you with me on what I'm saying here? I'm saying there's basically two ways to work this out. One is with Monte Carlo, and the other one is just by a formula. So we work out what the formula is. Maybe it's 2.1. Whereas the geometric Asian option here, it might be 2.5. Okay, so there's a difference between the two. What you do is you take that difference and you add it onto this. And hopefully you get a better answer, a better approximation to the one that you have. Okay, so that if you write that down, there you go. You see that? Let's be careful here. The elements that are starred are Monte Carlo simulations. Okay? This is the price of a geometric Asian. That's got by a formula. Okay? And as I say, these two are both different. Remember I said 2.1 and 2.5. Okay? Then I add that onto the one that the Monte Carlo said would work. Okay? And that gives me a better approximation to the price of an arithmetic option. Does that make sense? You have to think about it quite hard, but it comes together. And the idea is that, as I say, it gives you a better estimate, and it's very simple, because what have you got? If I know these values, it's subtraction and addition. That's all. So if I know what these things are, I just put them in. Of course, the problem with this technique is that you've got to use Monte Carlo. And if you're using Monte Carlo, this is a path-dependent option. So, path-dependent. And that means that the final payout of that option not only depends on the ST that you get at the end, but it depends on which path it's taken. Okay? And I've got to do that thousands of times for every path. Okay? So, in other words, when we were doing the Black-Scholes, all we needed was S big T. So Black-Scholes, Merton, all you need is ST. And then you subtract K. And then this comes blank. Simple. Okay? And we knew what we had a formula for ST. So we could generate it. But we didn't need to know what every possible value of ST there had been before the maturity. That's not the same for Asian options. Asian options, you've got to know every point of the path. Because every point of the path affects the payoff. So if you've simulated 20 or 100 paths, every little bit in that path has to be remembered. Okay? And then that has to be averaged. Then you work out the payoff, then you bring it back, and then you bring back all of them. So you're looking at thousands and thousands of pieces of data. Okay, so it's, as far as computation is concerned, it's not very good. And certainly you couldn't use it on the front desk. However, if you read the second part of the question, in a MATLAB environment, what is the main drawback of applying Monte Carlo to the price of an Asian option? That's just what I've said. The computation is very heavy. But there is something in the toolbox. Again, I mentioned this in the lab, and there it is there. We use the sim-by solution. So there is actually a function in MATLAB, in the financial toolbox, that what it does is it looks at all those values, and instead of generating the path every time you do a Monte Carlo, it remembers what the path is. And so it cuts down a lot of the work. Okay? So, I mean, it's a very useful way. MATLAB is very useful for doing this sort of thing. So, the drawback, as this option price is path dependent, we have to calculate the profile for every share price. Okay? And then remember, you have to do that. You'll simulate that 100 times, 50,000 times. Okay? So you've done it 50,000 times, you've got all these values. And yeah, so you've got, it's a real problem, the CPU, and it's time consuming. You can not mitigate it, but make it a little bit easier by using the paths for each option. Instead, we can use the function sim-by solution from the financial toolbox in that. You're welcome to go and research it and have a look at what it does, if you so wish. That was also mentioned in the lab. Is that okay? So we can use Monte Carlo to help get the answer to the arithmetic. And that's a recurring theme in the financial industry. You know, of course you need to know your mathematics and your statistics and computer science and so on, but a lot of it is, let's just use Monte Carlo. A lot of people haven't a clue how to use Monte Carlo or what it's about, but it's simple to use, so they quite happily use it. So it's not only in this sort of situation, they use it in lots and lots of situations, because it's simple. Simple to use. It's not particularly easy to maybe go back and do the theory of Monte Carlo. Yeah, that's a different problem.
Sorry, I would say we may use this difficulty by not one. Will that word?
Sorry, the first part of the second part?
Second part,
The second part.
first sentence, what would it be?
Instead, we may use the function. Is that the sentence?
No, we may use this difficulty by not, so that word.
Not regenerating the simulation paths every time. So you don't have to generate paths every time. That's what this is basically saying. And to say SimBy, I don't know what SimBy stands for. Simple bypass, I don't know. Are we okay with that? Again, please don't ignore it and hope it'll go away. All right. Oh, here we come. Question 6. It's in 2 parts. Describe the volatility smile, just in case it's also called skew for equities. Volatility's term structure, volatility surface, and their uses. So there are 4 questions in there. Okay, it's what's the smile? What does it mean by volatility term structure? What does it mean by volatility surface? And then finally, what sort of uses they have? Okay, so the 4 questions in that part A. Is that okay? So the answer, again, if you know your notes, the answer isn't too difficult. The volatility smile is the graph of implied volatility against the strike price. So if, just to remind you, it can look different. It can look like that. Okay, well that's your implied volatility, and that's the, is it the share price or the strike? A strike price, yeah. Yeah. Should be that. Oh, does that make sense? Remember, it's not. It doesn't have to look like that. That tends to be the currency markets. In the equity market, it tends to look like that. Okay. So we have different things to look at. So that's the smile. The volatility term structure is the implied volatility against the maturity. Okay, so we have 2. And in fact, you can take these 2 and take the Black-Scholes equations and change it slightly. And when you change it, you can actually take into account how volatility changes and the maturity changes over time. That will affect the price of the option. You with me on that? I mean, according to Black-Scholes, the implied volatility shouldn't matter. You just get some answer. But what happens is you can actually take into account what, if the volatility is changing, how that affects the share or the option price itself. What they call that, they call it a practitioner's Black-Scholes. And I think, if I remember right, if it's still there, it's, not that it's on the exam, but is it there? Let me just check this. No. You have the archive of CF966. You have last year's as well as this year's. But you have to go to the archive. Has anyone ever gone to the archive? In the archive, we would have considered it in the past, but it's not on the exam, so you don't need to worry about it. But again, I would like to point out, they call it the practitioner's Black-Scholes. So that's what they do in real life. You know, some people would say to me, why do we do Black-Scholes? Really, it's 50 years old. Surely there's better things to work out option prices. Well, that would be one of the best ones. The practitioner's Black-Scholes equation. Okay? So that would be something to look up. It would be useful maybe after the exams, or if you're thinking about dissertations and whatever, if you were looking for better ways to work out the values of these things. A trader is considering, sorry, I forgot there's a part B to this question. A trader is considering a speculative position, always dangerous, with regards to the current. Oh, sorry, we didn't finish that. Sorry, pardon me. That was naughty of me. I just talked about the volatility term structure and the volatility smile. What's a volatility surface? So the volatility surface is you have two independent variables, not just one. And the two independent variables are the strike price and the maturity. Okay? So that what you've got is you don't have a two-dimensional. Along the horizontal, you will have K, like that. And then coming out of the board, you have T. Okay, and then up here, you have implied volatility. And what happens here is you've got surface. So let me make that. Up here, you have some sort of surface. That's what it looks like. Okay. And to be honest, that's what the traders use. They use the volatility surface. How do they use it? Well, for a number of different things. And here I've sort of put together some. I'm sure you maybe could think of other uses for it, but here's some of the ones I thought of. It's used in pricing options. I mean, if I have a volatility surface, I can use that volatility surface. I can look at what the implied volatility of some of the options is near to the one you might be issuing. And from that volatility, I can work out what the price of a newly issued option should be. You with me on that? In other words, what I'm saying is we'll be using the Black-Scholes back to front. We would have all the usual things that are connected to a contract. You'll have K, you'll have S naught, you'll have R, T, sorry. And then if I know what the sigma is, I can work out the price. Now remember, this is a new option that you're putting out into the market. So you want to price it properly. So it'll be somewhere on this surface. Okay. Let's say the volatility. Let's say I've got T is there and K is there. Okay. And if I go up to my volatility surface, there's what it would say the volatility should be. Okay. You with me? Now, I won't have that in my volatility surface, that actual value. I might have these ones near to it. So what I do is I take an average of those, and that becomes my implied volatility for this option that I want to sell. So that volatility, say, it's 19.2%. So I take my 19.2%, put it in here, and that gives me the right price. If I get that wrong, then I can be taken advantage of, because either the option will be overpriced or it will be underpriced. And then that means there's arbitrage opportunities. You okay with that? So using it to price options is very useful. See, used to derive the underlying price distribution, that's a technical one. Used to predict future volatility, okay. And it can be used as an interpolation tool as well. That's kind of what I was, taking the average is kind of what I was, that's an interpolation tool. Okay, so that's just some of the things I can think of. I'm sure there's others. If you check John Holland's book or check the internet, I'm sure you'll get different uses as well. Are we okay? I think we're all about to dehydrate and fall asleep, but anyway. Okay, if there's no questions about that, I can move on. Right, this is question 7. Now, this is what I was talking about earlier. Question 7, part A.
You haven't said about part
Yes.
B. Like you haven't mentioned about part B.
About
The 6B.
that was it.
Oh,
Oh, okay.
no, you haven't.
Okay. A trader is considering taking a speculative position with regards to current volatility skew. Suggest, with reasons, a trading strategy to be adopted when a change in volatility skew is expected, with no clear indication of direction. Well, that's a thing like a straddle, strangle, things like that. I mean, if the volatility is expected to change, remember, if you look at a typical, let's say, one like that. Okay, so if you're going to hold that, well, why would you hold it? So there's your, that's probably the strike there. Okay, so one's a call and one's a put. And if the volatility is high, that means the price could be increasing or the price could be decreasing. Yeah? Are you with me on that? So you don't care which direction it goes in, as long as it goes far. Because if you fall in that region, that means there's your payoff. Is that okay? So if it's just the volatility that is what you want to bet on, then you don't care whether the share price goes up or the share price goes down. You just want it to move. You okay with that? Of course, the opposite would be told of the person who's selling the option. They don't want the volatility to be very big. So when the volatility is small, that means they get to keep the premiums. Does that make sense to you? Sorry, I must have missed that.
That's right.
Okay, any questions about that? Okay, I think this is the last question, question 7. Okay, question 7, part A. That's the thing that I was telling you about. Question 7, part A, you should be able to answer. Okay. The things like this can be technical and can be difficult to answer. Okay, so when you see something like that, give the desired characteristics of something, make sure you can do it. And it's in your notes. And if you want to take it further, you can go and look at John Hull and just jot down some of the things that you would expect to find when you looked at a model in interest rates or bond interest rates. Okay, so if I look at the solution, this, sorry, I did answer that one. In fact, I think I give you a more in-depth answer. But anyway, the one in the slides is fine. So there's the sort of characteristics you look for. arbitrage-free, interest rates are positive, mean reverting, realistic model, fits the data, easy to calibrate. I'm sure there are others, but I mean, these are brief. You've got this carrying five marks. So you don't have to go into a big, long explanation of things. Okay? Is that all right for everyone? Is there anything you want to ask? I mean, this is a good time to ask these things. If there is something, some doubt in your mind, please do ask. Okay? Right. Let's see the rest of the question. Write down the stochastic differential equation for the Hull-White model. Well, again, that's either you know it or you don't know it. Okay, so it's something that you can just learn about. And that's it there. But the thing about the Hull-White that's important is that this guy here, the mu, is a deterministic function of time. So mu is a function of time. And the alpha and the sigma are constant. Okay? That's the Hull-White model. And of course the W is standard Brownian motion. Just be careful about that. Sometimes when people are learning things like this, you learn the equation, which is very good. I mean, you need the equation. Without the equation, it's kind of a waste of time. But they never stop to think, what does R mean? What does sigma mean? What does alpha mean? What does mu mean? And so this bit here is just as important as that. So make sure you do both. Okay? Happy enough with that? And I would expect you to be able to do that for the CIR and for the passage check. Right, part C, B of TT is the price at time T of a zero coupon bond paying £1 at time capital T. RT is the short rate, Q is the risk neutral measure. Write down the equation for the price of a zero coupon bond using the risk neutral method. Now the thing about this, the answer to this is including the fact that the interest rate could be a stochastic process. So you've got to be careful. In the first term, when we were dealing with bonds, we assumed that the interest rate was constant. Okay? And it's not constant here. It's a stochastic process, so it's much more awkward to write down. So the price of the bond is given by the expectation with respect to the risk neutral measure of e to the minus the integral between t and big T. So in the past, in the first semester, you'd have quite happily written down b of t was equal to 1, because that's the final value, e to the minus r, t minus t. That's all you'd have written. But here the r is a stochastic process. Okay, and so it becomes an integral. All right, and it's with respect to ds. And it's about, we know the filtration up to time t. Does that make sense? Any questions about that? So you can see it's much more complicated than the first time. Okay, there's a lot of machinery going on there. Probably the hardest thing to get your head around, I think, is the filtration part. I mean, why do you have to have in that filtration? Well, essentially, it's a number line. When you draw that, your bond starts here at 0, and it finishes here at time t.
So you actually start the whole process at that point, as far as you're concerned. And what the filtration says is, I know everything that has happened up to that point when I buy the bond. Okay? Is that okay? So essentially, I know everything that happens at t equals little t and t equals big T. But everything in between, I don't know. That's uncertain. And that's why we have to write this thing down so carefully. Okay, so I would say to you, make sure you write that down carefully. Okay, you might say, oh, I'm a naughty boy because I haven't written in what those things mean, because I'm only after giving off to you about not writing down what each of the symbols mean. But if you read the question, the symbols are defined inside the question itself. Okay, maybe the filtration, not. So maybe I should have written in that curly F is a filtration up to the point T. Okay, but the rest of it would be defined in the question itself. Are we okay with that? I can guess what the the third part of the question is. Second part is the third part. It just says write down the last check. And if you look at that, and you look at that, you can look and say, oh, those two are the same. No, they're not. They differ, and it's a major difference here. The mu is a constant. So mu is a constant there. And that makes a big difference in the calculation. Okay. The whole white would be a much better model to use than the Vasicek. But it still suffers from the same thing, that the interest rates that it can predict could be negative. Okay. But they're more accurate than the Vasicek. The other thing is that it also must ask, what sort of process is this? Again, we go over it quickly in class, and a lot of people get confused. It's the Ornstein-Uhlenbeck process, referred to as the OU process. Does that make sense? It makes sense if you've done your revision. If you haven't done your revision, it'll make absolutely no sense whatsoever. And I think that must be the end of it. Yeah. Sorry, I'm going to have to annoy you yet again. It's student assessment of modules and teaching. I do apologize. Once again, I'm not supposed to look at these things, so can I have a volunteer that will bring them to Julie Pool? Okay, thanks. I don't know what. I think they're pretty easy to answer. Has your teacher paid you any money this term? Strongly agree with this. I think it's okay, there's nothing there. As well.
Oh, yes, remember I did say if you had any comments on the machine learning part, and that would be a good time to, I mean, I'm not saying write an essay on it, I'm just sort of, if I could hear your opinion. Sorry. I'll let people finish. Okay. Well, let me do this first, and then we can do that. Because I think people want to get out. It's just so hot, you know. Okay, as we're finishing there, let me just say, remember simple exam techniques. Arrive early at the venue. Please watch your time. 2 hours go in very, very quickly. So be disciplined. If there are 4 questions and more or less equal marks, make sure you only spend a quarter of the time on each question. I know it can be irritating as hell, and I was as bad. I remember spending nearly half an hour on working out the value of an American option because I knew how to do it. So it was a multiple choice question, and I could not get any of the answers on the multiple choice, and it really annoyed me, and I just kept at it and kept at it. I passed the exam, but barely, because I spent so much time just irritated by this question. So don't let yourself fall into that trap. Okay? Make sure you have the appropriate calculator so there's no awkwardness when it comes to that. Probably have to bring your student card and all that sort of stuff as well. And the best of luck. Okay? Please pass. I don't want to be marking stuff that's disastrous. With what they've done here, that should be a big help to you. But you've got to come and fulfill your side of the contract. I have helped, now you have got to work on this. When you are completely happy with those questions that you have there, and by completely happy I mean I can close a book and I can do them, then you can move on to other questions as well. Because it's not the only things that would be on the exam. There will be other stuff, but it's straightforward. Okay, if you've been doing your revision, you would do well. Okay, folks. See you on, and the best of luck. Do keep in touch. I'm on Facebook, LinkedIn, whatever. I've been on Facebook since it began, a million years ago. Well, I think it was 10 years ago, 12 years ago. Yeah, anyway. So, you want to ask about this?
It's a very simple question. What is that? FT?
Filtration.
Filtration.
Yeah.
What's that?
It's the it's
Filtration.
all the information of RT up until RT. So that's the diagram. Okay, it's the history, the information of the interest rate, you know, up to the point.
Okay.
Small t.
So it means all the history information of RT is.
So in other words, what I'm basically saying is any point before t, I know what the interest rate is now.
Okay.
So if But for this question, so I need to mention what is FT is, right?
FT is the filtration.
Filtration, and that's it. No need to explain anything. Like,
Well, remember, filtration is information. So, I mean, if you were to write down where FT is the information of RT, or up to. In other words, any time before little t, it's not a stochastic process. I know what it is. Okay, that's what this means.
thank you.
Okay, best of luck. Phew, it's very hot in here.
Yeah.
I think I've lost a couple of kilos.
Thank you.
Okay, you're welcome. I hope everything goes okay. It should do. I mean, I would imagine you'll do well and all the modules. I'd be surprised if you don't. Okay. You've got.
sees it. And so if there's any computers, TT or green explain to the meaning. Check the something GPG.
Gee.